So hi, my name is Florian, and I'm working also in the office in Denmark, and I'm going to present asynchronous programming in Dart. So a small outline, I will start with an introduction, compare the asynchronous and synchronous programming model, and remind you of how the asynchronous primitives work in Dart. I will then spend a little bit time on this new cool feature that we introduced in 1.9, Async await. Have a few slides on debugging, and then finish with a summary. So basically, an introduction of asynchronous programming versus synchronous programming can be reduced to two words, basically wait or yield. So basically, wait or don't wait. And I will give a small example of what I mean with that. Let's say you have a web server, and you get a request in. So if you are in a parallel synchronous environment, what you can do is you spawn off a thread, then you handle the response, and at some point, when you're done, you have a reply, and you return that response. Now, if you get a second request in, you just do the same thing again. You spawn off a thread, you handle the request, and at some point you have a response. And you do that for all the requests that come in. And if you do that, you have a nice parallel execution. You have, in this case, 5 threads, and you just run them. It looks kind of nice, busy, great. The problem with it is, clearly, the moment you have multi-threading, so parallel execution, you have race conditions. That's a classic problem. But it also is that it can also be that threads are expensive, especially if you use system threads. You only have a limited number of them, and it costs to build them up and run them. And it's also an inefficient use of the threads. And the reason for that is that, let's say we have this thread running here. It looks very busy. It looks like it's doing a lot of things. But what's happening most of the time in reality is that you have system calls. And during the system calls, you're just waiting for the system. You're actually not doing anything. And in the end, your thread is waiting for the system most of the time. So the asynchronous programming model in return basically says, don't wait, especially for these systems calls. We will call you back, so the system will call you back. So if you go back to these parallel tasks that are running in multiple threads, in the green and the blue ones here, in the parallel synchronous model, you just had the threads and they were waiting, whereas in the asynchronous model, you use one thread and you run the same tasks on the same thread, and you just basically, when you're waiting for the system, you continue running another task on the same thread. So even though, as you can see, it's not as fast in total because, well, you sometimes could run 2 things at the same time, but the thread makes you basically wait for the other one to finish. In total, given that we only use 1 thread instead of 2, we don't lose much time for that. The other thing that's important to note is that there's a typically asynchronous pattern in the sense that when you ask for something that takes a long time, so here it's called do something slow, you give that function a callback so that when it's done, it can call you back. And the more importantly, you go back to the event loop. So instead of waiting for the thing to return, you just finish all your things, you return from main, and then only at some point the event loop will come back and call you. So this has a few properties. For one, it's a better use of the threads. As I said, you use fewer threads for the same number of tasks. It's a cooperative model, so on the same thread, you're not going to have race conditions as if you do not yield. Obviously, once you yield, you let others do something on your static variables. It's callback-based, and there must be an event loop. And the interesting part about the callback-based and event loop is that this is something that fits very well in UI-driven, event-driven programs. So there's a nice fit of asynchronous program and event-driven, UI-driven programs. And that also means that reactive programs are more reactive. If you have a UI on one thread and you do asynchronous program on the same thread, well, because you do not wait and you do not block your threads, your program actually can still do UI while you are waiting for the system and so on. So now, this was the small synchronous versus asynchronous programming. How does it work in Dart? From the beginning on, when we designed the call libraries and when we designed Dart, we had asynchronous programming in mind. There's a nice library, Dart::async, that has lots of primitives, and I will show at least future and stream in the next slides. And we also use these asynchronous primitives all over the place. So Dart.io, Dart::convert, HTML, and islet, all of them consistently use the primitives that we have. Even though, as I said, HTML, for instance, is not really an asynchronous program, it's a UI event-driven programming model, but since they fit so nicely, you have a consistent model that fits just all over the place. So before I talk about the futures and streams in general, I want to give this small picture of these fundamental types that you have. In general, you have one single value. That's the single synchronous case. Or you return multiple values. That's the iterable case in synchronous world. And then in the asynchronous world, we have a duality. We have the futures for single values that are not there yet, and streams for multiple values. So here's the future from the Dart colon async. So really, a future is just represents a value that isn't there yet. And the way to interact with it, you have 3 basic functions on it: then, catch error, and when complete. All of them take a callback, the callback that you execute once you have that value. And all of them also return a future, which allows this nice future chaining that we have seen earlier since the beginning, basically, of Dart. Here's just a small example where we create a file. So we instantiate a new file, call create on it. Create itself returns as a future, so we can do this nice dot chaining. We do that .then. We add the callback. We also get a future back, which allows us to do a dot catch error on it, which then, depending on if we were able to create the file or not, prints created or couldn't create. Basic things, we have had that from Dart since 1.0. The stream, on the other hand, it's the asynchronous iterable. So as I said, we have the duality between single value and multiple value, and multiple values. So this is the stream is the asynchronous iterable. We have a sequence of values, and we have operations to manipulate and filter those values, just the same as in iterables. The main difference is that iterables are pulled and streams are pushed. And what I mean with that is that when you have an iterable, in order to get the next value, you really have to do something. You have to say, I want to move to next, I want to get the current. So you are the one in control. Whereas if you go for streams, well, here you have the stream element on click, you cannot say, give me the next value. You can say, yes, once you have a value, give it to me, but it's the stream that is it's the stream that is going to push the value to you. That is really the main difference, because if you now look at the API, here's the iterable, for instance. You have the iterator map where first for each, so all the things that we love on these iterables. If you look at the stream API, it's almost the same. It's we replaced the iterator with on listen, the callback, but all the other functions, map, where, first, and for each, they're all still there. Clearly, they cannot return the same values because they don't have those values yet, so they need to go to futures and streams in cases where we had iterables and normal values. But it's really the duality between an iterable and a stream. And this is really, really nice, because when we go now to this cool feature that we introduced recently, async await, the whole concepts really merge even more. And basically, when we introduced async await, the main purpose behind async await is to make it nicer and easier to program in asynchronous programs. And for that, the main point is improve the syntax. We want to make it easier to reason, write, read program of asynchronous programs. So let's go back to a small example, a web server in Dart, so no error handling here. The way it works in Dart, we bind an HTTP server to a socket, local host here, and that gives us a future back. And then we can basically register our callback with .then, say, well, once you have that callback, give me the server. I will then listen on all the requests that come in, so server is clearly a stream here. And then again, we pass in the callback, and we respond to these things. And unfortunately, even though we love these futures and streams, if we had done this in any other callback-based language, it would have looked almost the same. So instead of having the .then, we would have pushed the callback directly to the bind, but really it wouldn't have changed a lot. So there are still too many callbacks. We like the futures and streams, they're great, but there are still too many callbacks. And what we would like to have is something like this imaginary synchronous server, where we say, bind this to the server, bind the server, and once you're done, give me the server back. And then I run through all the requests, and I just handle them, and it just looks very nice, synchronous, straightforward, straight line code. And async await kind of tries to get there. It's syntactic sugar. You start with a modifier on the body, so that clearly means it's function local. And we have explicit points where we say, well, here we simulate, or we do as if you had written .then or listen. So let's go to the web server that I showed before. It's the same, nothing changed so far. The first thing we do in order to use async await is, as said, we have to have modifier. So we add the async on the body. So this is really just a modifier on the body. It doesn't change the signature of the function. The function still behaves the same as before. But once we have this async modifier, we can use primitives. We can use syntax, asynchronous syntax in the body. So in this case, for instance, we can say, we do not want the .then on the bind. We want to say, wait until it's done, and then we continue. Conceptually, I mean, it looks like it's a straight synchronous code we're actually waiting, but really this is not, this is the same as before. We still do a .then, it's just syntactic sugar to get there. And then if we want to get rid of the listen, we also can use await, and we have a similar syntax as before in the synchronous code and await for. So we take the server, the server stream, and then run over all the requests that come in and execute do the request handling. So this is really, it's still pretty much the same code as before, in the sense that it's still asynchronous, it's still waiting, but it looks much, much nicer. It looks now like the straightforward synchronous code that we wanted to have. So now a few of these details. So the first question, and it's a very easy question to start out with, what's the static type of an await? It's pretty obvious, but again, it's the easy one to start. If you have a future that returns a list of string, for instance, and you use it with an await, well, the static type of this await is going to be the generic type of that future. Nothing surprising here. The next question, a little bit more involved. What happens if you wait on a non-future value? And the way it works in Dart is that we just make it a future. So if you do an await on 499, for instance, well, it becomes an await of a new future.value of 499. The same is true for null. We just basically wait. The other thing is, does it work on closures? Yes. So even if you use the arrow-based or the normal curly-braced closures, you can just use async there. It just works the same way as if you had a method, just the same. And finally, and that one is actually quite interesting, the body of all asynchronous functions is automatically wrapped in a new future.microtask. And that has several consequences. So basically, if you see an async, you have to immediately think this is as if I saw a new future.microtask. And this has several consequences. One is, you will never have a synchronous error out of an async function. Because you have a new future.microtask, that new future.microtask will capture all synchronous errors, and you will only get errors back in the future. The other thing is that it means that the function yields immediately when you call it. So it will go through the event loop before it actually executes the body. And then it also gives us two nice answers for the questions of what happens if you return a future and the return type. So if you return a future inside the async body, well, it will just do as if you return it inside the future microtask. It will wait for the inner future to complete before it completes the other one. So that's basically, I mean, it falls out of this. Similarly, the return type of an async function is automatically future. So if you see an async on the body, it automatically means that the return type must be a future. There's just no way to get out of that. Yes, let's talk about the star versions. So going back to this table that we had before, we have these 4 different data types that you can return usually, or the most important ones. And now we always had the return type where we can just return a value. Now we just added a way to return a future of a value. By just adding an async to the body, now we can return a future out of the body. And in this section, I will show that we also have ways to return a stream or an iterable. So starting with the iterable, the sync star is the way to return an iterable from a function. So the moment you put a sync star on the body, you will return an iterable. It's the same as for future. The moment you have it, you will get that the return type is fixed. And sync star is actually pretty simple. It allows you to basically yield inside your body, and once you at the places where you yield, you push or you put the value in the iterable. This is done synchronously. So basically, once somebody starts listening or starts iterating over your iterable, it will start executing the function until it reaches a yield, and then only the caller that's called move next will get the value. And in this example, range 3, 6 does exactly what you expect it to do, 3, 4, 5, and done. So what we added with the sync star keyword is yield and yield star. So yield I just showed is basically pushing, or it's not really pushing, it's putting the value giving the value to the caller. A yield star pipes through a completely other iterable. So if we change the range function from before to become recursive, then then we can yield one value, the first one, and then recursively yield the remaining ones. Yes, there's a +1. So, and we can use yield star to do that. And really, it just takes the iterable that you got and pipes it through to the caller. So that means that we now have a way to return an iterable from a function just by adding a modifier on the body. And with async star, we also can do that for streams. So once you put an async star on the function body, you will return a stream, the same way as for the futures and for the iterables. And we have the same yield and yield star as we had for iterables, but we can also now use the await. So in this example, we have just a function that returns us the big files of a list of file names. We run over these file names one by one, open them, stat them, which is an asynchronous operation, so it will take the system a little bit of time to get that information. And then we just see if the file is more than 100K, and if it is, we push that value into the stream. So it's a basic, straightforward loop running over all the files. So since we are in asynchronous setting, we have the await and the await for, so that works nicely. And we also now have, since we are a stream, since we return multiple values, we have now yield and yield star. So this is really the combination of all the modifiers together. So again, a few things good to know. It's not going to be as much detail as the future one. So one thing you probably want to know is that both sync star and async star functions are not started before anybody is listening or iterating over them. So it really waits until somebody actually needs the values. The other thing that is important to know is that finalies are executed if a stream is cancelled. This gives you a way to handle resources. So you can have a resource handling like opening files, closing files in the finalies of a stream. And then just as an interesting note, because we discussed it for a long time, the yield eventually returns to the event loop. So in this example, for instance, you have a while true loop, which just yields 499, and you have different semantics possible. One is to say, we just continue running that loop and push the value into some buffer, and eventually you just die because you run out of memory. The other one is to say at every yield, we give somebody the chance to react to it. Or the third one, which is the one that we have in Dart, is to say, yes, you can push it in, but eventually we know that it will yield. It can be immediately, it can take some time, so it can buffer for some time for efficiency, but eventually you will yield. So basically what that means, you are allowed to write while true of an yield, and it will work. So this concludes the 4 different sections of this table. We have now ways to return values, futures, iterables, and streams just by adding modifiers to your function. And with that, I will talk a little bit more about debugging. As Lars said in the previous talk, debugging in asynchronous programs is really hard. There is clearly, obviously, the interleaved execution, but more importantly, the stack frames are lost. And even though I would have loved to basically be on the stage now and say, yes, we have the great solution here and everything is easy now, there's actually no real silver bullet. We are working on making things easier and better. As Lars said, we're trying to make that much better. But I mean, interleaved execution, there's nothing you can do. That's the whole point of running asynchronous programs. You want to alternate on your thread. And stack frames, it's really hard. But there's still ways to make it much better already now. And that's what I want to talk to in this section. Here we have a typical example of an asynchronous program. So it's just main calling chi, calling bar, calling foo, and foo is doing some asynchronous things, and then having an error. So if we look at the stack trace of this program, we will have a long stack trace, but in the end, so starting looking at the stack trace, there's a lot of things that we don't care about. So let's just clean that up first and look at the stack trace once we removed all the internal frames that we actually don't want. And after the cleanup, we are already at a point where we see, well, there's one stack trace, one frame, and it's foo. But it doesn't tell us where this foo comes from, why. Basically, it doesn't help us a lot. What's interesting is all these internal noisy frames that you saw before, the reason for them are zones. And these zones, while they are noisy and annoying, and we will try to make that better in future versions, they also help us to have sophisticated hooks to track stack traces and do other fancy stuff. I could do a full talk, 30 minutes easily on zones, so I will not go a lot of details. But if you want to track the stack traces, if you want to have a better debugging, what you would need to do is you create a zone description, then you fork the zone with that description. You intercept all the synchronous calls in that zone description again. You wrap the targets and store the tracing information on them so that when you come back, you can find it again. And then you install the information when you come back. And basically what I want to say is that this is extremely complicated. But fortunately for you, Natalie on the Dart team actually implemented this. So there's a stack trace package that is doing that for you. And this really helps a lot in asynchronous programming. And the way this works is, so if you go back to the original program that I had before, so this is nothing changed so far, just shifted a little bit down. The only thing you need to do to have an asynchronous stack trace is you import the stack trace package, and you call chain.capture on the function call where you want to get the asynchronous stack trace. And what happens in the background is now it will do exactly what I said before in the zones. It will register the zone description, intercept, all these kind of things. And if you now look at the stack trace now, it's not much better. But that's just, I mean, if you have sharp eyes, you will actually see that down there, here, somewhere, there is a foo bar in the G, which is the one that we want. So we are not done yet, but it's close. So what we need to do now is just have an on error, take the chain, and get the terse version of it. It's already in the stack trace package, it's already there. We just need to use it. And if we do that, then we get what we want. So I have bolded the things that I care about, so that's not part of the stack trace package. But we now have a main, we have the G, we have the bar, we have the foo. We see that there are asynchronous gaps to get there. We really have an idea of how did we actually get there. And this is what we want. This is what we need for debugging. And so what I recommend is if you have asynchronous programs and you want to debug them, try to use the asynchronous the stack trace package and see if that doesn't help you. So with that, I'm going to go to the summary. So really, what I want you to take away from this talk is that from the beginning on, we had Dart designed for asynchronous programming. So there's a lot of primitives and classes that have good semantics that work nicely in Dart. And with async await, since 9.1, we also have the nice syntax that goes with it. So not only do we have great classes and corollaries, we also have the syntax to go with it now. And then if you need to debug, I strongly recommend to use the stack trace package to help you figure out what's going on. Before I finish, I have to give some credits. Really not much in this talk is new. Almost everything has been done before. Futures are actually as old as 1976. At that time, they were called promises, futures, or eventuals. So they have existed, Lisp world, they have existed for a long time. And there are lots and lots of JavaScript packages out. So again, this has become popular recently. It's actually to a point where they have a standard of how do you need to interact so that you can use different promise packages so that they can interact with each other. So there's a standard now, a specification of how your promise package needs to behave. So there's a lot of future and promise going on. The streams are something we were heavily inspired by the reactive extensions in Rx, so that too comes from somewhere else. And the async await has been made popular by the .NET framework in version 4.5. And with that, I'm done. Thank you for listening. And I do think I do have a few minutes of questions.
So actually, if folks want to ask questions, I'll repeat them. And I do want to say, too, along with the debugging questions, so the unit test package and soon the test package, all of those things run using this stack trace thing. So actually, you'll notice in your testing situation, your stack traces should already look good because we took care of it in our testing packages for you. So again, if you see Natalie, buy her a whiskey. She likes whiskey. Any questions?
Yes.
Sir.
Okay,
so how does await for work with canceling subscriptions?
So await for automatically cancels the subscription if you leave the loop. So there is a try catch basically around it, a try finally, that makes sure that if you leave the loop in a non-standard way, we will cancel the subscription.
So people can use break or throw an exception, yes, and all that works.
Yes.
Way in the back.
is there a performance cost in the stack trace package? Can you use in production code? There is a performance cost. It's basically intercepting your asynchronous calls. Depending on how often that happens or when you use asynchronous calls, it might not matter that much because you are asynchronous anyway, so you're waiting for something. But there is an overhead.
I can add some detail too. So we use the stack trace package in pub, and the way we use it, because it's something you're dynamically enabling. When you're running pub normally, we just disable collecting the stack chains so that we don't take a perf hit. And then if you run pub in verbose mode, then we can just dynamically turn it on. So you can just, you can give the end user the ability to control that perf cost if you want.
What's great is there's that one entry point, right? So if I don't wrap that top level closure or that method with chain.capture, if you don't do that, you pay no cost. And so, for instance, in the test package, we do that wrapping, but in normal production code, generally not.
Yeah, I also want to add that that obviously since you capture the stack traces, you collect things, so it kind of, you cannot really run it in production forever. It will blow up. Does it work for Dutch JavaScript? I think there's one outstanding.
That's a Natalie question, and
yes.
I don't know if
We'll
Natalie's
find
in here right
Natalie,
now.
and she'll be able to answer for you.
If not, we should look at it.
30 seconds. And of course, if you haven't looked already, there's actually been a number of refactorings. You can look at the pub source code. Uses async await a lot. We've done some other refactoring.
A little.
Or a lot. They were the first customers because they do a lot of I/O. So if you're looking for examples or talk to me, there's a few of us, we can show you some code. The before and after is just mind-blowing. It's really fun, and it makes the code a lot more readable. So definitely take a look at it. And thank you, Florian.
Thank you.